In this short video, we will do some interesting stuff, and that is we will use concepts which we've learned in a number of chapters in the quantitative analysis section to, let's say, answer this question. And this question is, what will the distribution be of the sum of two random variables? Let's call them variables L1 and L2, each of which is uniformly distributed. For simplicity, what I'll do is I'll assume here that these two variables are uncorrelated. Let's even go stronger. Let's say they are independent. Now, you have L1, you have L2. Let's assume that the mean of L1 is mu1, the standard deviation of L1 is sigma 1. The mean of L2 is mu2, standard deviation sigma 2. Now, even before we go into distributions, there are some relations that we can write down which hold for any choice of distribution. And that is, if I were to write down my total loss as L1 plus L2, then I know that the mu p, which is the mean of this total loss, let's write it as expected value of LP. This is mu1 plus mu2, because mu1, mu2 are respectively the means of L1 and L2, and this relation holds no matter what your choice of distribution is for L1 and L2. Similarly, I am assuming independence between L1 and L2, and therefore sigma p square, which is the variance of LP, I can write it down as sigma 1 square plus sigma 2 square. Again, something which holds irrespective of the choice of distribution. Now, had this choice of distribution for L1 and L2 being the normal distribution, that means L1 was normally distributed with this as the mean, this as standard deviation, and so was L2, but with this as the mean and this as the standard deviation, you could write down that the distribution of LP is also normal, but this time with mean mu p and with standard deviation sigma p. And this property is this beautiful property which normal distribution has, and that is that it is stable under addition, which means the LP, which is the aggregate total of these two random variables which are individually speaking normally distributed, the LP also follows the same distribution. Now let's come back to our question, and our question was, what if L1, L2 are uniform? So to do that, let's do this. Let's assume that L1 is, let's say, uniformly distributed. The two parameters required are the left limit, which is, let's say, A, the right limit, which is, let's say, B. So L1 has its limits as A and B, and let's say L2 has its limits as C and D. That's what I am assuming here. So automatically, again, a quick recall of what the properties of uniform distribution are. It automatically gives me that mu1 is A plus B by 2 and sigma 1 is B minus A whole square. I should write sigma 1 square, that divided by 12. Similarly here, mu2 is C plus D by 2 and sigma 2 square is D minus C whole square by 12. So again, something which we've already learned. So this is about the statistics of L1 and L2. Now what about LP? Now LP still would follow these formulas, but what is not known to us is what distribution this LP will have. Let's try and see. So for doing that, let's use two approaches. Okay, that's again making use of everything that we've learned in the quant section. The first approach that we will use is the Monte Carlo simulation approach, and this approach, what we'll do is we will simulate the values of L1 and L2. We will add them up and we'll try and see what sort of distribution the sum of L1 and L2 has. Let's take a look at how do we do this simulation. If you have to simulate L1, which as we said lies in between these values A and B, you can simulate L1 using Excel, and the way you will do it is start with the left limit, that is A. This times do a B minus A, which is the entire, let's say, width or span of this L1, and that times a a random proportionate amount. So let's say rand, okay, the rand function in Excel. So this rand function, remember, is a uniformly distributed random variable between 0 and 1. So basically, intuitively speaking, if this rand comes out to be 0, then this expression boils down to a, which means that 0 corresponds to the left limit of L1, and if this u01 comes out to be 1, then you have a plus b minus a, and which is b. That means 1 corresponds to the right extreme of the distribution. So this is how you would simulate L1. Similarly, you can simulate L2 as the left limit of L2, which is c plus d minus c, and that times again another rand, which is independent of the previous rand. There is no dependence between these two rands, okay? So therefore, this is how I would simulate L1 and L2. Let's do it repeatedly. Let's do it many times. Let's add the two realizations of L1 and L2, and therefore we have many realizations of LP. Let's plot the distribution of LP and see what do we get. Now, this is where, the question gets answered, and the answer is the sum of two uniform distributed random variables. I'm assuming here that they are independent, is not uniform. Take a look at what we get. So this is what we get. So if I were to add these two random variables, we get a triangular distribution. The values which have been used here are these. So L1 here is uniformly distributed with left extreme as 50, right extreme as 150. The span between these two values is 100. So the L2, I am assuming it's uniformly distributed, and this time it starts from 100 and goes till 200. So the choice of these L1s and L2 here, basically it's done in such a way that the means are different. The mean of this guy is 100, the mean of this guy is 150, but the standard deviation is the same. So it's 100 divided by square root of 12. That comes to roughly 28 or something. So here again it's the same, 200 minus 100, that divided by square root of 12. So that's my case 1. So in case 1, I have assumed that the mean is different but standard deviation is the same, and this is the distribution that we get. Combine two uniforms with the same mean, with different means but the same standard deviation, what you get is a triangular distribution. That's what Monte Carlo simulation is telling us. But is this true for every choice of these distributions? Let's try and work out another example, and that is, this time let's pick L1 and L2 in such a way that they have different means and let's say different standard deviations. So let's do that. So in this second world, let me stick with the same L1. That means it's uniformly distributed between 50 and 150, and L2 again uniformly distributed, but this time let's do it as 100 and 300 instead of 100 and 200. So this guy, its standard deviation is much bigger. So when you do that, see, we don't get a triangular distribution. We are getting something like a trapezoidal distribution. It's like it's a trapezoid, right? The one thing which I sort of didn't mention in the previous page was that take a look at this distribution and intuitively make sure that this looks somewhat right, and that is, see, 50, 100. If both L1 and L2 get to their left extremes, LP, the lowest value which it can go to is 150. 50 plus 100. The highest value which LP can go to is 150 plus 200, and that's 350. Okay. Now let's come down. So back to this trapezoidal, again it's 50 plus 100, that's 150, left extreme, 150 plus 300, 450, that's the right extreme. But in this case, the standard deviations are also different, and hence it's not a triangular distribution, but rather it's a trapezoidal distribution. Now this was my approach 1. Monte Carlo simulation. Can we do it intuitively using a bit of math? Let's try and do it. So let's stick with the same example. So my example 1 was 1. So I'm writing down, let's write it from scratch. So I'm writing down LP for the choice of values which I was using, and that was 50 plus, remember how I had simulated it? It was a plus b minus a times a random variable. Let's call it u1. So it will be 50 plus 150 minus 50, and that is 100. This times u1, that's L1. Okay, this is L1. What was L2? L2 was 100 plus 200 minus 100, which is again 100 times U2. That means I can write down this LP as basically it's 150 plus 100. I can take it as common. It will be U1 plus U2. So if I am trying to get the PDF, the plots which I showed to you was the PDF, the distribution. If I'm trying to get the PDF of LP, I can get it via the CDF. So another concept which we can put to use. So let's try and do it. If I were to, let's say, write down the CDF, so what will it look like? Let's say for this value 210. Okay, the total loss to be 210. CDF is what? It's the probability that the total loss is less than 210. That's what the CDF would mean. And in this world, I would write it as, I just put down the formula of this LP. It'll come to, it's 150 plus 100 U1 plus U2 being less than 210. If you were to simplify this equation, it comes down to it's U1 plus U2 less than, take it on that side, it's 60, that divided by 100 is 0.6. Okay, so this is the equation which this guy boils down to. That means probability that aggregate loss is less than 210 is the same as the probability that U1 plus U2 is less than 0.6, where U1 and U2 are both uniformly distributed between 0 and 1. So this is what I need to find the probability of. If U1 and U2 can take any value between 0 and 1, that means on a graphical space, I can plot any realization of U1 and U2 in the form of a square. Okay, so that square would look something like this. If this one is U1, this one is U2, the square's bounds would be 1 here and 1 here, and this point would be 1, 1. Okay, and this would be like this. That means pick any realization of U1 comma U2 and it will lie in this square. It can be any point in this square. Okay, now if I want to find the probability that U1 plus U2 is less than 0.6, let's first plot that set of points for which U1 plus U2 is equal to 0.6. That will be a line which looks something like this. You can convince yourself that the equation of this line is U1 plus U2 is 0.6. Now, what is probability? Probability is like the number of favorable outcomes that divided by total number of outcomes. Here, both the number of favorable and the total number are infinite. Okay, we are not talking about a discrete distribution. We are talking about a continuous distribution here for both U1 and U2. Still, intuitively speaking, we can calculate this probability as the probability of you landing in a favorable area that divided by the total area. So total area is this square and that area is 1. The favorable area is actually this guy, okay? Because if this line has this equation, U1 plus U2 is equal to 0.6, the area beneath the line, the shaded area, would stand for U1 plus U2 to be less than 0.6. Okay, so probability that this thing is true is simply the probability of this shaded area that divided by the probability of this square, which is 1. Okay, so that's like a graphical route of finding this CDF. Let's try and see if this graphical route can help us explain the triangular distribution which we found in this case. Take a look at this. So for the choice of U1 plus U2 equal to 0.6, this is the blue line which I got. The probability of this happening, by the way, this is a mistake. It should be U2 here and U1 here. So probability of that happening is the area of this guy, this entire triangle, divided by the area of the square, which is 1. Now, if I were to plot the entire CDF, I will have to keep changing that choice of loss which I made, and that was 210. Okay, so as I increase that 210 number, I'll push this line like this. Okay, 0.6 was the case for 210. If you make it 240, maybe you will move towards the right like this. Okay, now when you move towards the right, see what is happening. The probability is the area of triangle divided by area of square. What is area of triangle? Is half base into height. So when I move this line out, the base is increasing and the height is also increasing. That means the area is increasing both on account of the base increasing and the height increasing. That means when this line moves out, the area moves up at a very, very rapid pace. It does increase, and the increase doesn't happen at a constant pace. It happens at a very rapid pace, at an increasing pace, okay? And therefore, this is for the CDF. Another concept now. Take a derivative of the CDF, you get the PDF. That means the rate of increase which the CDF is telling you is basically pointing to the CDF. Let me write it down. It will be basically the PDF is the derivative of the CDF. The CDF is increasing at an increasing rate. Take its derivative, the rate at which this is increasing becomes a constant. Okay, so therefore take a look at this. As this line moves towards this vertex, the area keeps increasing at a rapid pace because this triangle is ballooning up in size, and this ballooning up continues till we reach the green line, and that's where in our PDF we hit this vertex. Okay, we hit this guy. Now once you cross this green line, the area, which is my favorable area, now increases, yes, but not at an increasing pace. It actually increases at a decreasing pace, okay, and that too a rapidly decreasing pace, because this guy, you know, the triangle is now being constricted as you reach this vertex, and that's when this PDF starts dropping. Okay, this was how you can intuitively reason out what we found from Monte Carlo simulation using very simple intuition and math. Now, how about the trapezoid? The trapezoid, if you remember, was for a case in which the standard deviations were different. So I can write down LP in the case of the trapezoid to be equal to 150 plus, you can check this, it will be 100 U1 plus 2U2, because the standard deviation of the second guy was actually twice. Okay, so once you do this, the U1 plus U2, the line segment which we had drawn on this square, now changes. It's no longer this line segment which has a slope of -1. Okay, let's try and plot this line segment. This line segment now looks something like this. This is U2 and this is U1. Okay, so line segment is slightly slanted. You know, it's not a 45-degree line. Actually, it's not a -1 slope line. Take a look at this line. Again, start moving out. So as you start moving out, you will see that the area of the triangle increases at a rapid pace because the base is increasing, the height is increasing. When you hit this line, this guy, okay, see what happens. Till you know, from this line onwards, till you reach this line, the area which you are now calculating is the area of this triangle, this guy, and the area of this parallelogram. Okay, this is a parallelogram. It's between these two parallel lines, this line and this line. So when you move away from this line and reach till this line, how is the area increasing? Only the base of this parallelogram is increasing. I'm assuming this is the base and this is the height. So when I move from this line to the green line to this line to the brown line and to this finally purple line, what do I see? I basically see that the base is increasing, but the height of the parallelogram stays the same. That means the area is increasing, but it's increasing at a constant rate. It's not increasing because two determinants are going up together. Okay, so therefore this is the region, that the parallelogram region is the region which corresponds to, in the trapezoid, this region. So this is the region when your area is the parallelogram. When you finally cross this parallelogram and the line starts moving towards this vertex, the area to its left, I mean the area below this line, still increases, but it increases now at a decreasing rate. Why? Because we are decreasing now both the height of this new triangle, which sits on top of the parallelogram, and as well as the base of this triangle. Okay, so let's say this is the height and this is the base. Okay, so as we move towards this vertex, we are saying that the area increases but at a decreasing rate, and then this is the side, or this is the area of the PDF that we are covering after we have crossed this parallelogram. Okay, so what we've done here is that by using very simple intuition and math, we have rationalized as to why we obtain the triangular and the trapezoidal distributions in the two cases. So this short video brings home this point that when you take two random variables, let's say, which follow a certain distribution, don't take it for granted that the sum of these two random variables would also have the same distribution as the original random variables. That rule of thumb, it holds good for the normal distribution, and that's why the normal distribution is such a popular choice of distribution, and that's why, you know, we take this normal distribution in so many models that we work with. Keep one thing in mind as a quick recap: this property that the aggregate comes back into the same world of distributions where the original random variables started with is this property which is called the stability or the stable property of any distribution. That distribution is referred to as a stable distribution. Okay.